Okay, few last things on z-scores. We kind of gave some percentages or probabilities for z-scores with kind of whole numbers like between -3 and 3, -2 and 2, -1 and 1. But there's actually another set of standard z-scores, and these are ones that equate to kind of almost even percentages. So if we have 2.5% to the right of my z and 2.5% to the left of my minus z, that contains 95% of the z-scores. And in fact, there's this range of standard scores. So if we want to include 90%, it's between -1.645 and 1.645. As I mentioned before, 95% -1.96 and 1.96, 99% -2.575 and 2.575, and 99.9% -3.29 and 3.29. We'll actually use these a lot throughout the course, what are called standard z-scores and standard cutoff points. They can be a little bit controversial, the way researchers use these, and we'll discuss that as well. But these will be actually used quite a lot throughout this course. Okay, so we have a few more examples, and these are kind of in a table format. So let me just, we can actually just write on the slides. Let's just do a zip. Okay, here we go. And let's just select on there. Okay. Rightio. So we've got 3 midterm grades. And we have a midterm grade of 68 on psychology. So we think that's bad, but the mean was 65 and the standard deviation was 6, so we did better than average. Mathematics, we did exactly average. And geology, we did, even though we got a much better score, we did below average. So I think this example is trying to show the advantage of z-scores over raw scores in that z-scores are relative to the actual distribution. Okay, so this should be like really easy now. But let's just kind of calculate these. So we've got psychology. My z is going to be 68 minus 65 over 3. Notice the nice -6, sorry, the standard deviation. Notice the nice almost round numbers, which gives us 0.5. Mathematics, x minus mu is going to be 77 minus 77, so I won't even write anything down there. Sorry, I was going ahead of myself there. And for geology, we've got z equals 83 minus 89 all over 8, which is 6 over 8 minus 6 over 8 equals minus 0.75. So this actually now, and I've never reported z-scores to students, but this again, this will, except when I teach a statistics class, this will actually tell me that, okay, I thought I was doing well in geography, but in fact I'm below average. I'm minus 0.75 standard deviations below the average. And I was a bit depressed about my psychology result, but in fact I'm 0.5 standard deviations above the average. Okay, so back to the slides. So sometimes we actually want to rescale the scores. And here's kind of an example. And here what we're doing is we're going to rescale. We've got a set of scores where we were actually we've got scores for Alice, Bob, Carol, and Ted. The mean is 6 and the standard deviation is 3.18. So first we're going to calculate the z-scores, but we want to transform them into something called a t-score, which is a mean of 50 and a standard deviation of 10. So the next example I'm going to give is an SAT score, which is similar in that we look at where somebody is relative to the mean, and then we scale them onto a different scale. So let's go back to my pen and full screen this. Okay, so first for Alice. Okay, so for Alice, we have Z equals 10 minus 6 all over 3.18 equals 1.26. For Bob, we have Z equals 9 minus 6 all over 3.18 equals 0.943. And then Carol, now notice 9 minus 6, 3 minus 6, that's 3 minus 3, so it's just actually going to be the opposite, but negative. And then Ted is going to be minus 0.314. So here we have 0.943 minus 0.943 and minus 0.314. And then the t-score for Alice, it's just this value, 1.26, times by 10 plus 50. So this one was going to be times by 10, 9.43 plus 50. 59.4. We'll just stick with one decimal place to be consistent. And then Carol minus 9.43. So just get how I did that again. I'll just do the first one. That's going to be 10 times 0.943 plus 50, which is sigma Z plus mu. So this is the calculation we did before to do the inverse. And then Carol minus 9.43 plus 50. And that's going to be 40.57. And then Ted minus 0.314 plus 50. So it's 50 minus 3.14 is going to be 46. Okay, this is going to be 50 minus 3.14 minus 0.314 times 10. And so that's going to be 0.86, 46.86. So again, just to do the last one, so you've got it, that's going to be 50, the mu, plus minus 0.314 times 10, which would be minus 3.14, which would be 46.86. Okay, and we got a very similar example next. And this is basically just transforming, doing the same, but with SAT scores. So we have then this time they have a mean of 500 and a standard deviation of 100. So let's just quickly work through this. And there's kind of a shortcut to this. So let's just write down the z-scores. This is exactly the same data, so we don't have to calculate the z-scores again. So we got 0.94 minus 0.94. We'll do it with 3, because we're multiplied by 100, and minus 0.314. And you can see 626, that is going to be 500. We can do it either way around, doesn't really matter. Plus 100 times z, 100 times 1.26 equals 626. Now notice that these numbers are actually just going to be 10 times the previous ones, because that was 50 and 10. So this is going to be 594, and we'll just stick to the whole numbers. This is going to be 406, and this is going to be 469, and that is going to be, let's just go back to the previous ones. Okay. And you see, actually, if we'd kept to some decimal places, then this would be one decimal place. This would be 40.6, and this would be 46.9. So we just literally multiply everything by 10. Okay, so sorry for the slightly inconsistent number of decimals, but I think you get the idea of how this works. That we can actually go either way with these z-scores. We can convert certain kind of different scales into z-scores, but we could also transform z-scores into new scales based on this position in the standard distribution, for example, with educational measurements such as SAT scores. And that's all for today.